Jnanam paramam dhyayam. Knowledge is supreme.
So, how did we, I am just revising what we have done. How did we start off the course? We started looking at how does linearity arise in real life, and that was systems of linear equations, right, trying to find solutions of systems of linear equations, and the method given by Gauss, that is eliminating one variable at a time, we wanted to formalize it. So, to formalize that, we brought in what is called the matrix representation of a system of linear equations. So, that looked like A x is equal to B, right. A is a m cross n matrix, right, m equations in n variables. So, x is the vector which is components written as a column x 1 x 2 x n equal to B, B 1 B 2 B m. So, that is A x is equal to B, where A is m cross n, your variable x is a vector which is n cross 1, right, one column, n rows and n one column, and that is equal to, right, B 1 B 2 B m, that is m rows and one column, right. So, matrix form. So, the question is, how do you solve A x is equal to B, right. So, we said the method of Gauss is nothing but reducing the matrix A to row equivalent form, or a specialized one called reduced row equivalent form. So, what is a row equivalent form? Row equivalent form of a matrix is that by elementary row operations, right, elementary row operations are, you can multiply a row by a non-zero scalar, you can add one row to another, or you can interchange two rows. So, these are called elementary row operations. By doing these operations alone, you can bring your matrix to a special form. You are doing something on the rows, and the row equivalent form is essentially says in your matrix, right, there will be some bottom rows which are going to be 0 possibly, right. There are some non-zero rows and some rows which are identically 0. So, suppose there are r rows which are non-zero, they are at the top, n minus r are at the bottom, right. So, it says that this r, we give it a name called as the rank of the matrix, right. And so, there is a number r such that r between 1 and n, such that bottom r, top r rows are non-zero, bottom rows are 0. Now, in why a row is non-zero? Because somewhere a non-zero entry is coming. So, how do we describe that? You look at a row, first spot the first non-zero entry, it comes at a column called P 1. Look at the second row, the first non-zero entry comes at a place called P 2, column number P 2. So, the condition is P 2 should be bigger than P 1. Each next row non-zero entry should be coming in a column which is on the right side of the earlier one, right. It may not be immediate right, it will be somewhere on the right. Okay. So, that form of the matrix is called row equivalent form, and you can further do row operations. So, that in that column the only one non-zero entry is there, right. There is a non-zero entry, below that everything is 0. So, that entry is called a pivot. In that, everything at the top also you can make it 0 by elementary row operations. So, in pivotal columns where the first non-zero entry of a particular row is coming, by row operations further you can make that is the only non-zero entry, everything else is 0, and that non-zero entry also you can divide by that constant and make it equal to 1, right. So, that is called the reduced row equivalent form of the matrix. Then we looked at applications of this. One, when a system is consistent or inconsistent, the rank. So, take the A x is equal to B, take a augmented matrix A B, right, reduced to the row equivalent form. If the rank of A, right, is same as rank of B, then the system is consistent, otherwise if it is bigger one more, then it is not consistent. When it is consistent, that means what? There are r pivots among the r n variables, there are r pivots, right? P1, P2, Pn are coming in the columns. So those pivotal variables, their values are obtained from the non-pivotal variables by giving non-pivotal variables arbitrary values and backward substitution. So take at the bottom row, right, compute the pivotal variable in terms of the non-pivotal ones, give them arbitrary value, put back and get your all solutions, right. That is finding all possible solutions. And then we also said that solving a system Ax is equal to b is essentially equivalent to solving the homogeneous part of it, Ax is equal to 0. What is the difference? You find one particular solution of Ax is equal to b somehow and find all solutions of Ax is equal to 0. So general solution is obtained by taking one particular solution, adding to it a solution of the homogeneous system, right. So that gives you all. That also brought okay, so we will come to that a bit later, but row echelon form also gives you a method of checking whether a square matrix is invertible or not, right. So what if it is going to be invertible, that means there should be a unique solution for Ax is equal to b, that is same as equivalent to saying rank should be full, and that is same as saying when you reduce row echelon form, that should be identity. So a method of checking is take a n by n, put along with the identity matrix n by n and do row operations to a and do the same operations to identity also, and try to find out what is the reduced row echelon form of a. If this becomes identity, the next portion gives you the A inverse, where identity has changed to, right, that becomes A inverse. That is finding what is how to check whether something is invertible or not, and at the same time computing the inverse also. So that is application of row echelon form, another one. And then we looked at matrices, and we looked at the row space and the column space, right. They are all subspaces of Rn or Rm, right. What is a subspace? It is a subset of Rn or Rm, so that in itself it is closed under linear combinations, right. That is a subspace. Okay. For example, in R2, if you take a line passing through the origin, that is a subspace of R2, right, because if I take any 2 points and add them, we will be somewhere on the line again, right, scalar multiple also. So that is a subspace. So row space, column space, and then we looked at what is the dimension of the row space, dimension of the column space, and we said both are same, that is same equal to the rank of the matrix, right. And what is dimension of a space? That involved what is called a basis and the number of elements in a basis. So we said every subspace, right, of a vectors of Rn or Rm will have a basis. What is a basis? You take linear combinations of a subset B is called a basis. If you take all linear combinations of elements of that, that should give you all elements in that space, and it should be minimal. You should not be able to reduce number of, you should not be able to remove some elements from that. So it is a minimal set of generators equivalent to, it is a maximal linearly independent set. So those were equivalent ways of describing what is a basis. And then we proved, we did not prove, we said theorem that any two bases have the same number of elements. A vector subspace can have different bases. For example, R3 itself has different bases, right, we gave many examples, but the number of elements in a basis will always be same, and that is called the dimension of the space, right. So we had dimension of the column space, dimension of the row space, and we also had dimension of the null space. Ax is equal to 0, that was called the nullity. So we had the theorem, rank nullity theorem, the rank plus nullity is equal to n, right. So that was the rank nullity theorem we proved, and that had some applications, namely every matrix or every okay, we came to linear transformations, rank nullity theorem for linear transformations meant the dimension of the row space plus dimension of the range space, right. That as a consequence, okay, I think more systematically we looked at matrix multiplication as a linear map, A applied to x equal to y, that is a linear operation on the domain x y. So, you can call that as a linear map induced by a matrix, and conversely every linear transformation from one vector space to another, of course vector space is subspace of R n, gave rise to a matrix representation of the linear transformation. So, how was that obtained? Say T is from V to W, V of dimension 2, W of dimension 3, right. So, V the dimension 2, it has a basis element V 1, V 2, W dimension 3, it has basis elements W 1, W 2, W 3. So, take V 1, take the image of V 1 under T, that will go to some vector in W, but that should be a linear combination of W 1, W 2, W 3. So, T V 1 is a linear combination. So, those scalars which are coming in the linear combination, that gives you the first row. T of V 2 again a linear combination, that gives you the second row. So, take the basis elements in domain, each one take the image, write it as a linear combination, you get the corresponding columns of the matrix representation, right. So, that is a matrix representation of a linear transformation, and then as a consequence of rank nullity theorem, we said T is 1 1 is same as saying T is on 2 as maps, right. So, that is what we proved. So, that was linear transformations, matrices of linear transformations, rank, basis, dimension. Then we looked at generalizing the notion of angle in vector spaces, right, because there is a notion of angle dot product in R n. So, that we brought in the notion of perpendicularity, two vectors are perpendicular if their dot product is equal to 0. So, we said given a basis, can we generate a orthonormal basis out of it, right. A basis is linearly independent set of vectors which generate everything. Orthonormal is those every orthogonal collection is also linearly independent automatically, right. That is a simple property that we proved, and then we said that, but every linearly independent need not be orthogonal obviously. So, how do you get from linear independence to orthogonal, that is Gram-Schmidt process. So, given a linearly independent set, one by one iteratively you can generate a basis which is a orthonormal basis, right. So, once that is obtained, that means what is the advantage of orthonormal basis? It says that the coordinates of a vector, see every vector is a unique linear combination of the basis elements, right. Every V is sigma alpha I V I, where V 1 V 2 are the basis elements. These alpha i's are unique, right. That is what we called as the coordinates of the vector. These unique coordinates are immediately known if the orthonormal basis is given, because it is just a dot product. If you take the dot product on both sides of a particular V I, the right side is V I V j, everything will vanish except V I V I, right. So, that means advantage of a orthonormal basis is that coordinates of a vector are immediately computable, right, if your basis is orthonormal. That is why we prefer to have a orthonormal basis whenever possible, and that is Gram-Schmidt process, right. And then we looked at the particular case that given a matrix, how can we make it similar to a diagonal matrix. That means finding a invertible matrix P such that P inverse A P is diagonal. That was the diagonalization process or the problem. We said this leads to computation of eigenvalues, computation of eigenvectors, and checking when are the eigenvectors linearly independent and they form a basis of the underlying space. If the matrix is n cross n, that should form a basis of R n, right. So, and we computation of eigenvalues that led to determinant of A minus lambda I. So, because A minus lambda I, you want to find a solution of that, a non-zero solution, that means A minus lambda I should not be invertible, right. Then only it is possible. If it is invertible, only unique solution for homogeneous system, that is a trivial one. If you want a non-zero solution, then determinant of A minus lambda I should be equal to 0, because it has to be singular, and that means solving the polynomial, finding roots of the polynomial determinant of A minus lambda I, that gave you the eigenvalues. How do you find the corresponding eigenvectors? The solution of A minus lambda I applied to x is equal to 0, you have to find x. So, finding solution of the homogeneous system, where the matrix is A minus lambda I, and for that we know, go back to row echelon form and see what is the rank, what is the nullity. So, null space you want all possible solutions, right. You can find the dimension of the null space, those many linearly independent eigenvectors you can obtain. And we proved a theorem that for distinct eigenvalues, eigenvectors are linearly independent. For a general matrix, the eigenvectors corresponding to distinct eigenvalues are linearly independent, right. Now, the question is only inside for a particular eigenvalue, if you look at all eigenvectors, right, they form a subspace. Okay. The question is whether dimension of that subspace is same as the number of times the root is repeated or not. So, number of times the root is repeated is called algebraic multiplicity. The dimension of the null space of A minus lambda I is called geometric multiplicity. Whenever the two are equal, your matrix will be diagonalizable, because that says you will be able to find as many linearly independent eigenvectors as the number of times eigenvalue is repeated, right. So, that was diagonalizability of an arbitrary matrix. That may or may not happen. So, the condition is you should have eigenvalues, each eigenvalue algebraic multiplicity should be equal to the geometric multiplicity, right, and there should be n eigenvalues, and that happens if your matrix is a real symmetric matrix. For a real symmetric matrix, you are assured that there will be as many eigenvalues as is the dimension, that is n cross n. So, n is the dimension of the matrix, there will be n eigenvalues, even if algebraic multiplicity of each will be equal to geometric multiplicity, that is also part of the claim, that is part of the theorem. And thirdly, you can find a orthonormal basis of eigenvectors. For any two distinct eigenvalues, the eigenvectors are perpendicular to each other, but inside only they will be linearly independent for each eigenvalue. Using Gram-Schmidt, you can orthonormalize them also. So, that is what we did today. Okay. So, that is our, in 5 minutes, 10 minutes I have revised the whole course. So, next 2 lectures what I am going to do is I am going to look at abstract vector spaces other than subspaces of Rn or Rn itself. They also come in your courses later on. So, we will spend some time on them. Okay. So, we will stop today, we will not go to them today itself. So, today's lecture ends here. Okay.